Okay, so I may not have had any examples in the last set of notes, but boy, am I making up for it now. Um, so now we're talking about planes. So we're going to start with vector equations of a plane. Here is the way they read on your formula sheet. So first we have just the traditional vector equation of a plane, and then we have using the normal vector and then the Cartesian form. Most often you will probably see the Cartesian form, but you might have to convert to the other ones. So two planes are either parallel or intersecting at a line. To be parallel, their normal vectors must be collinear. So we're going to go ahead and start with this first example and start with A. So A reads that plane 2 and plane 3 are parallel, which parallel means that they would, that the directional vector of the second plane would be equal to some scalar times the directional vector of the third plane, and that it has no common points. So I have to prove both of those. Okay, so we're going to start with just the directional vectors, which if I want the directional vector of the plane, then I just have to pull the coefficients. So D2 is 1 to -1, and D3 is 2, 4, -2, which is the same thing as 2 times this first one. So normally you would do that in between step to show your work, but I'm not going to waste my time doing that. And then we have to check that there are no common points. So really I can just multiply the first one by 2. So I would have that 2x plus 4y minus 2z is equal to 0 if I multiply the first one by 2. But I also in the third plane have that it's equal to 1. So that means that there are no common points, and you would write this all out in words. There are no, you would write the steps multiplying by 2, and then you would say, so there are no common points. And then because of both of those things, you can say, therefore, plane 2 is parallel to plane 3. Okay. Now the second one is showing that they tells us that they are intersecting, and they want us to find the equation of the line. So for the first one, really we're just rearranging these equations and plugging them in so that we can get rid of variables. So when I do part B, the first one I see easiest to do is going to be from the plane 2. I can solve for z and then plug it into the first one. So plane 1 now becomes 2x minus 3y plus 5 times the quantity of, and then I'm going to solve plane 2 for z, which is x plus 2y is equal to 1. And z plane 2, z is equal to x plus 2y. Okay, from there, I can now isolate the y variable in plane 1. So now I can say that y is equal to 1/7 minus x. There's algebra involved, but by now I would really hope that y'all can do that. And now I'm going to plug it in for y in my second equation. So now I have z is equal to x plus 2 times the quantity of 1/7 minus x. And then math happens. Once you get there, we should have now that x is equal to lambda. We're going to put this into parametric form. Y is equal to 1/7 minus lambda, and z is equal to 2/7 minus lambda. Basically what this means is that because it's a line, it doesn't matter what that one x variable is, because it will always be on the line. And then whatever we make our X value, that will change our YZ value. So that's why it's that specific intersection. Okay. All right, moving on from there, we have another example. This one's wanting us to use our formula up here, the equation of a plane using the normal vector. So that's the second equation. But we don't have the vectors yet, which means that first we have to come up with what the vectors are. So I'm going to have my U vector be A, B. And I'll just write this in the normal form first, I guess. So we have I minus 2j plus 2k. And then we have V is AC, which is 2i minus 3j minus k. Okay, so now I'm going to use that formula from the equation of a normal plane. So I can say that -1, -2, 2 cross 2, -3, -1 is equal to -4, -3, 1. So this was to get, my equation of a plane because it's perpendicular. So now I need to use the normal formula. So we have, scroll over. So now I have -4, -3, 1 dot XYZ. We're trying to figure out what this point is here, what that vector is. And then we have -4, -3, 1. Dot, and then we need our equation. I can pick any of the 3 points. I'm just going to use point A because it's right there. We have 1, 2, 1. Okay, so now I get to do some fun maths, and what you should end up getting for the equation of the plane is -4x minus 3y plus z equals -9. If you need to go back and look at your past notes to practice, that's fine. If you divided out a negative, you could do that as well. You would have 4x plus 3y minus z equals +9. Either one is acceptable. That's just writing it in a different form. Okay, moving on. Now we're going to talk about 3 planes. They can intersect at one point at a line, or they can be, all 3 of them can be parallel. So I went ahead and skipped the basic problem and jumped to the one that has a little bit more of an IB influence, where we're looking for a separate perimeter M. It requires you to think a little bit further ahead. So we're looking for the value M so that the planes intersect at a singular point. So the first step is to just find the place where they, the first 2 would intersect. So I have, again, similar to the one we just did, the first example, part B, we're basically going to repeat that same process. So what I end up with, I'm going to use, in order to get rid of a variable, you could either solve for X in the second one and plug it in, but I think it's easier in this case. I see that +2z and the -z, so I'm going to use elimination. So if I were to multiply the first plane by 2, I would have plane 1 is 4x minus 6y minus 2z equals 10. And plane 2 is x plus 5y plus 2z equals 6. So from here, now if I use substitution, I can isolate these variables to get first 5x minus y equals 16. I've eliminated the z variable, and then from there, I can now isolate my y, and I have y equals 5x minus 16. So now what I will do is go back to my plane 1 equation and plug this in for my y value in order to and isolate my z variable. So I know that's complicated sounding, but it's not that bad. So if I solve plane 1 for z, I get z is equal to 2x minus 3y, and instead of y, I'm going to plug in 5x minus 16. And then, sorry, keep it going, minus 5. Okay, from here, I get that z is equal to negative 13x plus 43. Okay, so now that I have all of these pieces, I have that x is equal to lambda, and so I can plug them back in. And I'm going to go ahead and skip that step. You could write it out, x equals lambda, and then y equals 5 lambda minus 16, z equals negative 13 lambda plus 43. But I'm going to go ahead and jump ahead to the equation, which would be, switch colors for a second, r equals negative 16j plus 43k plus lambda times all the ones that would be associated with the x. So I would have just 1, 5, and 43. No, and 13. Okay. From there, here's where it gets a little bit tricky about you needing to know the definitions. So the concept here is if it only intersects at one point, then I need to make it so that the directional vector times the normal vector is not equal to 0, meaning that they are not meaning that they're not perpendicular. So what I can do here now using this information is to say that I'm going to take this vector, so that would be 1, 5, negative 13, dot this vector here, so that one would be 4m negative 4, and say that it cannot equal 0. When you solve that out, you should get that m cannot equal negative 56 over 5. And that's that one. So this is a concept that would not be on your formula sheet. It's something that you need to know and understand. So if I want them to intersect at one point, I want those to not be equal to 0. But if I want them to intersect on a line, I do want it to be equal to 0. So let's take a look at one of those examples where we do want it, that dot product, that scalar product, to be equal to 0. So again, I skipped ahead to one with a little bit more of an IB orientation of trying to find these additional values. So the first step that I see is easiest, I think for this one, I would use substitution. So I'm going to solve the first plane. I'm going to solve it for y. So when I use plane 1, I have that y is equal to 1 minus 2x plus 3z. Now, in theory, you could solve for any variable, any way that you want to. These are just, you get better practice once you do it more often. Looking at plane 2 now, I can plug in those values. So now I have x minus 2 times the quantity. Instead of y, I'm going to plug in what I just solved for, minus 2x plus 3z plus 2z equals 4. From there, I can now say, solve that bottom equation, isolate it for the variable x in terms of z. So now I have y equals 1 minus 2 times the quantity of 6 plus 4z over 5, which is the answer we're going to get if you take the time to do the math, plus 3z. That here we have x. When we solve that equation to the left, if you solve it for x, you should get x equals 6 plus 4z over 5. Not too bad. So now I can rewrite it in that parametric form. I'll go ahead and do it this time. So we should have x is equal to 6/5 plus 4/5 lambda, y equals negative 7/5 plus 7/5 lambda, and z equals lambda. Okay, so this is my new form of the plane. And now I can find my directional vector from this, or direction vector. And so now I know that D, I'm going to give it a vector symbol above it because I can't boldface it. My directional vector would be equal to, it would be 4/5, 7/5, and 1, but I know that I can factor out the 1/5 in the form of a scalar. So remember when we had the lambda times a vector, you can factor out a constant, basically, the greatest common factor. So if I wanted to factor out a 1/5, I would now write it as 4i plus 7j plus 5k. It's the same thing, just a different way of writing it. I think it's a little bit easier. So now if the line is in the third plane, so if I want it to be a part of this third plane up here, then the directional vector is perpendicular to the normal vector. So my directional vector dot my normal vector is going to be equal to 0. So they would have to be perpendicular. That's just a part of the definition. So from there, let's go ahead and do that then. So now I have 475 dot something is going to be equal to 0. You could come up with different answers here. There are going to be multiple answers. Usually they are multiples of one another. But the easiest one that I see, I know this is kind of air quotes cheating, but you can figure it out. But I noticed that 7 plus 5 is 12, which is a multiple of 4. So I'm going to use 3 for x and then solve it. So you could come up with lots of different answers, but try plugging in 3 for x in this formula and see what you get. You should get that that vector is 3, -1, -1. Now, again, you could have lots of different vectors coming up. But I like the ones with whole numbers, and that's just the one I noticed first. So now I take any point on the line from line 1 to figure out what D is. So this is my A, B, and C, by the way. Those are my A, B, and C values. So now I need to figure out what D is. And the way I do that is by finding any point here. Now, the easiest number I can think of to plug in is 1. So I'm going to do that. I'm going to plug in 1 for lambda. And now I'm going to have a point. And my point would be 2, 0, 1. when lambda equals 1. But you could plug in any value for lambda that you wanted to. I just think that this was easy. But if you wanted to plug in 0, you could have 6/5, -7/5, and 0 if you wanted to. But I just like this one because it ended in whole numbers. But you can definitely do it with fractions, no problem there. Okay, so now from here, what I'm going to do is use that point and plug it into my directional, to my normal vector, sorry, excuse me, to the plane. So I'm going to plug it into the plane. I should have, let's see, we have 3 is my a value times x, in this case is 2, minus -1 times 0 and -1 times 1 should be equal to 5. So this is my d value now. Now that I've figured out what my d value is, I can rewrite this equation. So it would be 3x minus y minus z equals 5. And that is my final answer. A lot of work, but I don't think it's too bad once you get in the habit of what definitions you need to use. The biggest one to remember in these cases, when you're working with 3 planes, is if you want them to intersect at a point, then the dot product of the normal and the directional vector is not equal to 0. If you want them to be intersecting at a line, then it is. I can explain why, but I think it's easier if you just memorize it. Okay, moving forward. Goodness gracious, this is a long lesson. Okay, so the line and planes can have different relationships. You can read, you can see that picture. I think it's just pretty straightforward. But we're going to go through this example with numbers, and it will do each of those things to show how they're all related. Okay, so let me get over here. We have the first one. We have that the steps are going to be the same for each one in this particular case. Step 1 is going to be rewriting it in parametric form, and step 2 is going to be plugging it into the plane. So let's start with the first line. When I rewrite it in parametric form, I have x is equal to -1 plus 2 lambda, y is equal to 3 minus lambda, and z is equal to -2 plus 3 lambda. You might want to write this smaller. I'm just tired of zooming in and out. From here, I'm now going to just plug in those values to the plane. So I have 2 times x, which in this case is -1 plus 2 lambda, plus 3 minus lambda, minus z, which is -2 plus 3 lambda. Equals 3. Okay, from there, algebra happens. You should end up getting that 3 equals 3, which means that L1 is in the plane. So this would be an example from the picture up above. It would be line N. Okay, so now let's look at the second one. So for the second one, again, the first step is rewriting it in parametric form. You should get that x equals 2 plus lambda, y equals 2 lambda, and z equals -1 plus 5 lambda. You're going to follow that exact same process of plugging it into this plane equation up here. I'm not going to do all of that. However, I will tell you some of the answers that you should get. You should get that lambda is equal to 2. Once you get that lambda is equal to a specific number, you're going to plug it back into these x, y's, and z's, and that will give you the specific point where they intersect. So that is 449 should be your final answer. So this has one common point. So this is an example of line M in the picture above. All right, last but not least, we have line 3. So x would be equal to negative lambda, y is equal to negative 5 plus 4 lambda, and z is equal to negative 3 plus 2 lambda. Okay, from here, again, you're going to plug it into the plane equation. What you should end up getting when algebra happens is that negative 2 is equal to 3. But we know that these two things are not the same. Therefore, we know that they are parallel. So that would be an example of L. So that's that. Okay, moving on to the next sets of examples. Once you get the hang of these aren't too bad. The first one is an angle between two planes. An angle between two planes is always acute, so we're using the absolute value. And then we just find the angle between the normal vectors. So the first step is just to find our normal vectors. So I have that the first normal vector would be 1 to negative 2. And the second one would be 2, negative 3, negative 6. From here, all you have to use is your angle between two vectors formula from a couple days ago. So that formula, again, just to remind you, is cosine theta equals vector 1 dot vector 2 magnitude absolute value over normal 1, normal 2. Okay, so in this case, you should end up getting that theta is equal to 1.18, 3 significant figures. I'm not going to sit here and do the math for you. I think by now you should be capable enough. All right, so moving on to the next kind, very similar process. It's an angle between two lines, also always going to be acute, so we're using the absolute value. And then all we have to do is find the angle between the directional vectors. Now, this is really nice. It already has it in the fractional form, which means that we know the directional vectors right away. So in this case, the first directional vector should be 3, 4, 12. And the second one is 2, negative 1, negative 2. I know it's negative 1 because this is the same thing as 5 plus y over negative 1. So you would normally want the y out in front. So y plus 5. Okay, anyway. So for this one, you follow the exact same formula, exact same process, and you should get that theta is equal to 0.971. Pretty easy, pretty straightforward. All right, this last one is the angle between a line and a plane. Now, there are two different ways to do it. One of them is definitely takes a lot longer. The first method takes a lot longer, but it is the one that is associated with the formulas that you already know. Like, you don't have to learn extra things. The second one is definitely faster, but you don't have the information in front of you on the test. So I will show you both ways. You don't have to write them both down. You can pick one, or you could write them both down. I recommend watching both of them and then deciding how important it is for you to learn each one. Okay. Whew. So for this first one, the first thing I need to do is I'm going to put this into parametric equation form. This is just part A. This is the same for both of them. Sorry. So the line would be the same thing as x, y, z equals This is 2 lambda minus 3, 4 lambda plus 5, and 2/3 lambda minus 1 gross. From here, we're going to plug it into the plane equation. I'm not going to do that for you other than telling you the answer. So you're just going to plug in the x, y, and z here and solve, and you should get that lambda is equal to 3, and then you plug that back in, and then you get your point. And so the point of intersection is 3, 17, 1. Okay. All right, now here is where there's the split. So I'll start with method 1, which is the one that you should know more about and will look familiar to you. So for method 1, the first thing we need to do is find another point on the plane. So I'm going to plug in 0 for lambda because that will give me whole numbers. So when lambda equals 0, then I have point A would be -3, 5, -1. Okay, so now I need to find the line perpendicular through A. And that would be 5 lambda minus 3 negative lambda plus 5, 4 lambda minus 1. Sorry, I got the last 3 numbers without the lambda from here. And then the other ones are right here, 5, -1, and 4. That's the perpendicular. Sorry. So from there, you should plug it into the plane again. You're going to plug it into the plane equation. And once you do, you should get a really ugly number. It's going to be that lambda, that is the worst lambda I've drawn all day, and I've had some bad lambdas. Lambda is equal to 13 over 21. From here, now you should plug it back in, and you get an ugly point of intersection. But that point of intersection would be, we'll call it F, just for fun. 2 over 21, 92 over 21, and 31 over 21 once you plug them all in. So now I can come up with my directional vector, which is, I'm going to factor out, sorry, it's the directional vector of line 1. I really hate that 2/3, so I'm going to factor it out because any parallel one to this one also applies, and this would just be parallel. So instead, it's going to be 3i plus 6j plus k instead of ugly fractions. So now that I have my directional vector, I can now find PF, or I don't need my directional vector yet, but I'm going to find my second vector, PF. The point from part A was, 3, 17, 1. From there, I can now find this vector, which would be also ugly, but it is, I'm running out of room, sorry. PF is -61 over 21, I minus 265 over 21j, plus 10 over 21k, which again, you're just doing F minus P. It's not that bad. It just happens to be ugly numbers. I don't like this, so I'm going to pull out the -1 over 21. And once I do that, See my final two vectors. Let's write them in a little bit nicer of a form. My directional vector then would be 3, 6, 1. And my PF vector would be 61, 265, -10. From here, I now just get to use that cosine formula. So the cosine theta, and what you should end up getting is that theta is equal to 0.300. Now, all of that super ugly, gross numbers, but it's the same process that I've been doing the whole time. The only thing that I added was the PF step, coming up with our second point of intersection. However, here's method 2. So method 2 is where you find the angle between the normal vector of the plane and the direction vector of the line. So when I have method 2, I have that the directional vector, I'm going to do the same thing and pull out the 2/3, which leaves me with the directional vector of 3, 6, 1. And then I have that the normal vector is 5, -1, 4. This is the normal vector of the plane here. Now, if I do both of these, I have two vectors, but it's not cosine theta. I have to use sine theta. And the reason why is because the angle between the line and the plane is complementary to the angle between the directional vector of the line and the normal to the plane. So I can use the same formula, but I have to use sine theta instead. So it would be dot n over dn, which still comes up with the same thing of theta is equal to 0.300. Now, obviously, this is 10,000 times faster, so much less room for error, but that means that you have to memorize not only this piece, but I would encourage you to remember why it's this piece. So I'm going to say it again slowly. We use sine theta because the angle between the line and the plane is complementary to the angle between the line, the directional vector of the line, and the normal vector to the plane. Okay, so I would be prepared to write the reasoning. They may not even give you credit without the reasoning. Not that you have to write all of those words, but you might need to write because it's complementary or something like that. You definitely need to associate it that this is the formula only that you use for the angle between a line and a plane. All right, I know that was so much information and I am exhausted, so I'm sure you are too. But I'm going to go ahead and end this video.